So whether if you are more like a side channelist or a cryptanalyst or implementer, maybe you find something interesting in this presentation. So let's start with an overview of the context. Sorry for the ones that already know all this NIST standardization thing. So in 2017, the NIST started a standardization campaign for choosing post-quantum algorithms to implement in the future. So in the round one, the NIST emphasized on assessing the quantum and mathematical security. So at that stage, there were 69 candidates, and 23 of these 69 candidates passed to the round two. And then there, the community paid more attention to the performance and implementations of these candidates. And finally, the third round, and we hope that it's the final round. It was announced recently, so last summer. And so now every aspect of the security matters. Side channel, timing attacks, misuse resilience, and also all the previous characteristics like mathematical security, quantum security, etc. So now there are 7 finalists, 3 for key encapsulation mechanisms, no, 4 for key encapsulation mechanisms, and 3 for signatures. So we will get back to them later. But first, let's focus on lattices. So one important problem on which many schemes are based is called learning with error, or LWE for short. So it can naturally be seen as a linear system solving with noise. So given a pair A, which A is a matrix, and B, which is equal to AZ plus E, where A is sampled uniformly at random and E and Z are sampled following a small distribution T, so typically a Gaussian, for example. Then the challenge of this problem is to find Z or equivalently E. So this is assumed to be a hard problem. In this presentation, we denote S, the secret, as the concatenation of Z and E in a vector. So here we do not see, with this definition, we do not see how it relates to like a lattice structure and why we say that it's a lattice problem. So let's see it from a geometric point of view. So if I draw this S, which is still ZE, we can see it as a short vector in the lattice, where we define the lattice, which we denote lambda. And we can so embed it from the matrix A, the vector B, and the modulus Q. And so once we have this lambda, S is the shortest vector of this lattice. So this is called the Cannon embedding. And now we see that it has a geometric point of view. And to find Z, a solution can be to find the short vector of this lattice. Or we can take this problem as saying that we want a vector in the green zone here, for example. So let's go back to the schemes from the NIST standardization process. So in pink, I've put all the multivariate polynomial schemes. So there is only a rainbow, which is not in a very good position right now. So maybe later it will not be in the winners. There is also error correcting codes in green. So only Michaelis for the key encapsulation mechanisms. And so the 5 others are based on lattices. So not exactly with LWE that I showed previously, but on so module LWE, which is a variant of LWE, or module CIS, which is also another lattice problem, or NTRU, which is a third lattice problem. And so for those 3, we say that there are lattice problems because the best cryptanalysts use the search for short vector in a lattice. So for both categories of LWE and NTRU, we can build from them a LWE variant. So from module LWE, we can create or build a LWE instance, and from the NTRU, we can create a LWE instance. And then when we have that, this can be estimated, and we can have an idea of the cost of an attack. So when we want to estimate the cost of an attack, this allows to quantify the security, since it's the best known attack, and so we just compute the complexity and assume that the scheme has a certain security, like 128 bits of security. So more precisely, let's take LWE algorithm, like in a black box. This problem can be embedded into a short vector problem, as shown previously. So there is a lot of literature on this subject to really estimate the cost of an attack. And so the cost of finding a short vector, presented in these three papers, it can be, sorry, the best solution is to run an algorithm which is called BKZ. And in this presentation, actually, we do not really know how we can just consider that it's a black box and that it has a parameter, and this parameter is beta. And it gives an idea of the complexity of this algorithm. So the higher the beta is, so beta is a block size, the longer the algorithm takes. So we just need to know that. And so there are several possibilities to convert this block size beta into a bit security, which is called the cost models. So actually, it's an equation that relates this beta into a bit security. So for example, 128 bits of security. And once we have that, it corresponds to the amount of work for a key recovery. So this is often like affine or linear, the conversion from beta to the bit security. But the community is not unanimous on these cost models, actually. So we can roughly say that the block size should be divided by 3 to get the bit security, but there are many discussions on these cost models. So here we consider key recovery attacks. And in these attacks, there are some hybrid attacks where some attackers are willing to leverage some extra information in addition to the mathematical security. So there are, for example, design constraints where we have actually extra information on the structure of the secrets. There are side channels information where we measure the power consumption or the timing of the device running the algorithm. There are quantum algorithms where we just use Grover acceleration. And there are decryption failure attacks where we leverage the fact that some decryption may fail. So let's see, for example, a side channel attack, how it works. So we have our LWE algorithm, and then we make some measurements from it. So it can be represented as traces from consumption. So we have several traces. And then we have a measure that says that the minimum number of traces needed for a full key recovery. So for example, we can say that when we have 100 traces, we can get a full key recovery. So we can see that it's different. It's a different approach than assessing the mathematical security. And so our question was: is it possible to have something hybrid that takes the best of both worlds? So on one side, we think that we assume that we have a little side channel information, or side information in general, and we cannot get a key recovery right away, but we can include it in the lattice reduction attack in order to decrease the mathematical attack. So in order to decrease the amount of work for a key recovery. Then we have a hybrid attack, because on one side we have some information, some side information, and on the other side we have a cost of a lattice reduction, which is a little bit decreased. So actually, to do this was done in previous papers with ad hoc techniques. And the missing part that was really generic was this part. So including the side information into the lattice reduction. So this is what we did in this paper. So we integrate side information hints into lattice reduction attack to predict at the end the security drop. So let's see the outline of the talk. So I will start by presenting the theoretical framework of this paper, and then I will demonstrate how this works in practical practical instances with the demonstration of the SAGE tool. And then I will show how it can be applied for different settings. So it can be applied on the side channel attack. And in that case, we have a lot of side information, and it allows to decrease the mathematical security by a lot. I will also apply it to real-world specifications where we have some design constraints, some information about the structure of the secret, so a little bit of side information, and it allows to have a more precise estimation of the attack. So it decreased it slightly decreased the mathematical security. And also for decryption failure attacks. So here, the more failures, the easier the mathematical attack gets. So let's see the theoretical framework. So I will just give an overview with geometric intuitions. So first, we need to transform our LWE instance into a distorted bounded distance decoding problem to get more flexibility on the parameters. So now the center and covariance of the target secret can vary. So instead of having a center 0 and covariance, which is identity, so just a disk, now we have so a center that is arbitrary and a covariance that is denoted sigma. And so we see that it corresponds to an ellipse where the eigenvectors are the directions of the ellipse. Ellipsoid, sorry. Yeah. So mostly the balls are replaced by ellipsoids for having more flexibility and to be able to include more secrets, more hints on the secret. So here is the original technique for assessing LWE instance. So as I said, we embed it into a short vector problem, and with a short vector problem, we apply lattice reduction, and we have this beta that allows to get an information about the security. So now we add some extra steps in order to include our hints. So we have our DBDD instance, which is the variant of LWE I presented in the previous slide. And we have these hints that are side information in the form of an equation containing the secret. And we will integrate each hint one by one until we have a DBD that is very distorted because it has many hints. And so to get something that is more standard for a short vector problem, we have to homogenize and isotropize it and transform it into a short vector problem. So first, let's see how the first arrow works. So we have our LWE instance with EZ that are the solutions. And so E and Z are drawn with the distribution key. And so the instance LWE is like that. And we can say that the vector S, which is equal to EZ and 1, is a short vector in the lattice that is defined as lambda 0 here, which is just all the vectors x, y, w, such that x plus y A transpose minus b w is equal to 0 mod q. So we can verify that EZ belongs to this lattice. It just corresponds to the equation B equal AZ plus E. And then with that, we have also sigma 0 and the mu 0 that corresponds to the distribution that are close to the distribution key, except that in the last coordinate, which is 1, it's 1 with 100%. So the variance is 0 and the average is 1. So it's just that. Then we have our DBDD instance, our original one. Now let's see how we integrate the hints. So let's first focus on perfect hints. For the perfect hints, we assume that we know a vector V such that S inner product with V is equal to L. So it's as if we knew an equation, like a linear equation between the coefficients of the secret. So in dimension 2, for example, we can know that ZE inner product with 1, 1 is equal to 0, which means that we know that E plus Z is equal to 0. So it's just knowing a constraint like a linear equation between the coefficients of the secret. So we don't know S, but we know this V, this V and this L. So geometrically on the right side, we can see that, so there is this S in red and the V is given by the blue arrow. And so if we know L, we know a hyperplane where the secret S is. So we know L here. And so we know that the secret is on the orange line. We know that the secret is around here because S inner product with V is equal to L. So actually, we can just eliminate all the other dots because we know that the secret is not there. So we intersect the lattice with the hyperplane and we project the distribution on this hyperplane. And at the end, we see that we have a DPDD instance still, but we have one dimension less, and so it becomes an easier DPDD instance. So each time we have a perfect hint, we have a easier DPDD because we lose one dimension. So now let's see the modular hints. So it's similar. We know V, L, and K such that S inner product with V is equal to L modulus K. So here there is a modulus K that appears. So it's as if we knew that Z plus E, for example, so here ZE inner product with 0, 1 is equal to 0 mod 2, so which means that we know the least significant bit of E, for example. But we have a lot of flexibility with L, K, and V. So for example, it's knowing an equation, a linear equation, modular something. So here, if we represent it as geometrically, so we have our vector V here. So S is contained into a union of hyperplanes. So for example, for L0 here, we know that S is in one of these on one of these orange lines, because it cannot be equal to something different, so modulus K. So here, as previously, we remove all the dots where the secrets cannot be. And so it's called the sparsification because the lattice gets sparser. So it's an intersection between all the hyperplanes and the original lattice. Here we see that we cannot lose one dimension. We still have the same dimension, but the lattice is sparser. So the instance is still easier. We have less possibilities for the secrets. Okay, for the modular hint. Now let's see the approximate hints. So here we assume that we know that the secret S inner product with V is approximately equal to L. So here we do not know exactly if it's equal to L, but it's not far, and so we assume that there is a Gaussian noise around this value L. So it's as if we knew that, for example, E is approximately equal to 0, or it's equal to 0 plus or minus 1. It depends on so there is another parameter, which is the standard deviation of the Gaussian noise. Yeah. And then here we know a hyperplane, and we know that S is not on this orange line, but it's not far because it's in this line plus or minus some Gaussian noise. So the only thing that we can do is modifying the distribution to focus our attention around this hyperplane. And so with that, the instance is still easier because we have a more accurate distribution at the end. And so one important comment is that if the Gaussian noise of around this L tends to 0, then we end back into a perfect hint. Into a perfect hint, because then we know that S inner product with V is equal to L. So that's it for the 3 hints. There is a last hint that is a little bit different from the other hints. it's more of a construction that we needed to compare with the literature. So we call them short vector hints. And it's just adding the information that we know a short vector in the lattice. So there is no information about the secrets. So typically we can say that the Q vectors, so vector with Q and the zeros, Q somewhere and 0 belong to the lattice because it's a lattice modulus Q. And so it corresponds to ignoring one LWE sample. Because sometimes when we have too many samples, we need to ignore some in order to have a more accurate security estimation. This is mostly to fit with the dimension volume trade-off that is presented in this paper. Yeah, so it was mostly to capture this trade-off presented here, and we cannot always integrate them. It depends if the Q vector belong in the lattice or if we have modified the lattice too much. In that case, the security cannot be more precise. We cannot use this short vector to have a more precise security. So yeah, we integrate them one by one. Each time the instance gets easier, and when the instance gets harder, we stop. So here it is. Now we have the last step. So consider that we have our DBDD instance that we integrate many hints. So we have a DBDD that is distorted with a different center. There are some dimensions that are lost. It is sparsified, for example. Now we cannot apply a short vector short vector SVP reduction right away. So we have to first make an homogenization. So we put the center the center at the center of the lattice. So it's done by these equations. So we recenter it, and then we isotropize it. So since it's not a Gaussian anymore, we like distort the lattice in order to have something that is a disk and not an ellipsoid. So with that, we just multiply by square root of the sigma matrix, and then it distorts the lattice. Once we have that, we can assume the security. And so we have everything. So I presented all the bricks for this technique. So we can introduce some side information on the secret that corresponds to these three red equations. So SV equal L, SV equal L plus modulus Q, and SV approximately equal L. So we integrate this, and then we decrease the security, and we can get like a security drop by decreasing our beta, which is the parameter of PKZ. So here are all the bricks, but maybe some of you are disappointed because here we can only integrate linear equations on the secret. And this does not capture any side information because sometimes we have something that is binary, or we know the number of bits of the secret, like the Hamming weight. So it's a first step, and there might be some other hints to integrate, but with some tricks we can integrate more information than these equations. So I will show you one of these tricks. So let's consider that we have a secret that has its value between -5 and 5, and they are represented by signed integers. So when it's negative, it has many ones in the register. So after a poor analysis, an attacker might learn the Hamming weight of, say, S0. So we know that Hamming weight of S0 here is equal to 2. Once we have that, we have only two possibilities for S0. Either it is 3 or it is 5. Because the others are, the negative ones have many ones in the register. So once we have that, it's not immediate how to integrate it in the lattice with a linear S inner product with V equals something, but actually we can with two hints. We can use a modular hint, so having S inner product with so the canonical vector 1 and all zeros, just to target the S0. It's equal to 1 modulus 2. So which means that S0 is an odd number, which is true because 3 and 5 are odd numbers, but there are others. There is 1, there is -1. So it does not capture very well, but at least it removes half of the possibilities. But in addition with this hint with another hint, which is an approximate hint, there we can capture more information. We can have an approximate hint that says that S0 is approximately equal 4 plus or -1. So with the variance 1. Then if we combine the fact that S0 is odd and S0 is equal to 4 plus or -1, we see that we capture pretty well the information of being S0 it belongs to 3, 5. So we can sometimes integrate Hamming weight information by having some tricks on combining several hints together. So now I will present briefly the SAGE tool, just to show you how it works. So the SAGE implementation started as a proof of concept in this paper, but it ended up in a pretty evolved tool, I think. So we started with a full-fledged version, so on the left, where here we keep the basis and we compute every projection, every intersection of the hints. So we make all the computations. So on the one hand, it was possible to estimate the security drop and or the residual security so efficiently by computing beta as its exact value. And on the other hand, it is also possible to run BKZ algorithm on a specific instance. So once we have integrated on the hints, we can run the attack and recover exactly the secrets. However, for a large instance, this is not possible because the lattice schemes are designed so that BKZ cannot be run. It's too costly. So for the large instance, actually, we do not need all these full calculus. We do not need a full-fledged version because the attacks are never feasible. So we would rather use a prediction mode. And so here it only keeps the crucial parameters to estimate the security drop, which are the volume of the lattice and the dimension of the lattice. So on the theory side, we had a bit of extra work because we had to prove that when we integrate a hint, what is the impact on the volume and the dimension without computing the basis, without computing how it works on the basis. So we did that, and now we have like the prediction prediction mode, which is way faster than the full-fledged version. But we also added a last version that is suited for hints that target coefficient by coefficient. So instead of having a hint that targets all the coefficients, so that's what we call diagonal hints that target one coefficient. So typically targeting S0 and S1, etc., but not mixed together. In that case, we do not even need to keep the full matrix sigma. We just need to keep its diagonal. And then the computations are faster. So for example, it goes from 5 or 6 hours for the fast prediction mode when we have like 1,000 hints to 5 minutes for the fast prediction. So it's quite helpful for this. So yeah, we have these three classes that allows several use cases. Let's see how the prediction works versus the experiments. So we have our prediction that computes the beta, the parameter with the hints, and so we can see that it's pretty close. So in red, it's the experiments. So we run a real attack with BKZ. So here we are in a range of parameters where we can actually run the attack with a lot of redundancy, and we have the average beta for certain hints integration, and we have the prediction in black. And so we see that it's accurate. It's not exactly perfect. And maybe it's because of we made some assumptions to compute the impact of the hint integration into some the volume and the dimension. So maybe it's because of that, but it's still pretty accurate. So there's for the 3 types of hints: perfect, the modular, and the approximates. Okay. So let's see how the tool works without hints. So this was filmed on my computer. Does it work? Maybe I have to. Yeah, okay. So I just wrote some parameters for LWE instance. So n equals 70, m equals n, and the q is the modulus. So just 3,301. And then I introduce a distribution for a secret S. So yeah, here S is the Z actually, because our S is the concatenation of S and E, but yeah, there is a naming problem here. And so here we have our matrix. We generate our matrix A, our vector B, and the DBDD instance by initializing from LWE instance. So we do that. Up. And here it estimates the original security. So it estimates no, it first builds the instance, and then we will estimate. So we estimate beta, which is the parameter of the attack, and delta, which is another parameter of the attack. And so we see that beta here is equal to 45. 45.40. And so we will run the attack and see when it stops. And so we run like a BKZ that increases the block size until it finds the secret, until it finds a secret that has the correct norm. So it goes up and up, and we will see that it will stop around 45. Maybe I. So yeah, 39. Almost finished. Yeah, so success with 42. So we can actually run the attack with the full-fledged version. So this was filmed on my computer. So now let's see with some hints. So we have our same instance here. With 45, beta 45, but we so I introduce 4 vectors v0 to v3 that are random. It doesn't matter. It just simulates some extra information. And so we simulate the information that we have. So actually this corresponds, so this 37 corresponds to V0 inner product with the secret. And this is V1 inner product with the secret. So this is to simulate some extra information that we might have. Now we will integrate it into the DBDD instance. So we integrate perfect hint. So V0. So we say that it's equal to 37. And then it integrates it. And so we see that this is to check that it's a worthy int, that it has not been already integrated. So we have the dimension, and the most important is the beta, which is 41 now. So we have lost several units for beta. And then it decreases again for the second, it decreases again for the third and the fourth. And now we will integrate the modular hints. So we do the same, but with V4, V5, and V6. And instead of having a hint, so what we call the leak, like a perfect leak, we take it modulus 2 here, modulus 3 here, and modulus 4 here. And so we have, so we integrate them. So don't forget that we have already a beta equal 30 here. And so actually it decreases a little bit, but a little bit less. And intuitively, we can see that because when we know modular information, it's less. We have less information that as if we knew the perfect one. So that's normal that we do not lose so much. So we lose 0.4 here, etc. And so at the end we get to 29. And now we will integrate the approximate one. So instead of having the leak, I add some noise artificially, like I add 2 here and I take -1 here. And so I will integrate the approximate hint. And here, so this is the variance of the noise that I added. So here we see that we lost a little bit, and then we lost again, etc. And so at the end, the attack estimation is 27. So we went from 45 to 27. So the attack should be easier. Oh, damn. And I can run the attack. So let's go back. So we run the attack. And so it succeeded at 24. So around 27, which corresponds to roughly the estimation. So we see that before we stopped at 40-ish beta, and now we stop at 24. So integrating hints is beneficial for the attacker. So let's see now in a concrete example, because here I was simulating the side information. So now let's see how it can be attacked in a side, real side channel attacks. So let me just drink a bit. Up, let's go. So to test our scheme, we wanted to use some data that our perfect use was to have some team that was having some side information, but cannot lead to a full key recovery because the information was not enough, and so maybe yeah, we wanted something like that, and we were lucky to find it in a paper in this paper, so a paper from Boss et al. From Psych 2018. Actually, in this paper they presented two attacks. A first attack that did not succeed because they had some information, but they said it was too weak for a full key recovery. So perfect setting for us. And they presented a second attack that was successful, and so we focused on the first one. So the target is Frodochem, which is one of the key encapsulation mechanism from the NIST. So there is a side channel part, so I will not enter into the details here, but we assume that the attacker obtains an a posteriori distribution on the secret. So for example, we know that S0 is equal to 2 with 80% probability, and S1 is equal to 0 with 100% probability, and so etc. And we also have, for example, for S0, we have a second hypothesis that has, I don't know, 10%, etc. So we know an a posteriori distribution. Then it's really easy because we can just transform them into a posteriori distribution, approximate or perfect hints. For example, the first one, we integrate an approximate hint. And for the second one, we integrate a perfect hint because we know that it's 100% probability. So with this, since we had it for each coefficient, we add n approximate or perfect hints. So this was a lot of side information. And beside, we added some other idea by guessing when the probability is higher than 97%. So we assume that it's not an approximate hint, but a perfect hint. And in that case, we have a probabilistic attack because sometimes it's not the right value. And so we had to compute the success probability too. So this allowed a high decrease of the mathematical security. And so it allowed to have an attack. Let's see a concrete example. So here are the bit security of two sets of parameters that are called NIST1 and NIST2 of Frodochem. So here I write the bit security, but do not forget that once we have this beta, we have to use a model to convert beta into a bit security. So here I chose this model, so the 0.265, but any model is fine, and we can just stay with beta before. But for having more like concrete example, I converted it. So for the NIST1, we see that without hint, it corresponds to the security, the claimed security, so 129 bits of security and 187. And so once we integrate the hints, we see that it decreased by a lot. And it decreased even more when we add some guesses, like so we tolerate a success probability that is not 1. And so, for example, for NIS2, we have an attack of 2 to the 78 with 0.65 success probability, so more than one time out of 2. So this is like an application, but actually there exists some similar applications on the entity computation of crystal kyber and dilithium that we did with an intern in ANSI. And so it can be applied in different settings for side channel attacks. So as we can see, we can really decrease the mathematical attack, and so we can finish the attack. Well, not in practice, but we have an attack that is below the claim security. So let's see for the real world specifications. So now assume there are some schemes. So NTRU, LAC, or round 5, which is so NTRU is still in the round 3 of NIST standardization process, but LAC and round 5 are not in round 2, in round 3. It's a bit confusing. So they use ternary secrets, so which means that the secrets have value between -1, 0, and 1. And actually, one important constraint is that they have a fixed amount of plus or -1. So actually, it can be written in the equation here. So the sum of all this SI, so all the coefficients, is equal to L, which is a parameter of the scheme. So we can see that there is like a very natural perfect hint here, because we have S in a product with 1, 1, 1, 1, 1 equal to L. So we can just with the design of the scheme, we can have a little bit decrease a little bit the security. So here we have a really slight amount of side information that is actually for free because it's from the design, and then we decrease by a tiny bit. So we see that here are the parameters with or without hint. So we lose actually 1 bit of security. We lose a little bit more because, for NTRU because we had some other techniques. But yeah, it allows to have a more precise security, even if it's not a lot. So let's see now a little bit the decryption failure attacks. So here I will enter into more details. So assume that so all the lattice-based key encapsulation mechanisms have non-zero failure probability, which is a new feature that was introduced by lattice-based schemes. So how does it work? We have our LW instance. So here it is in a really simple example. So A and B are sent through the public channel, and then another attacker embeds its message into two equations, so B prime and B prime. It's sent through the public channel, and then to decrypt, so the other party makes some computation. At the end, it has, so Bob or the server has the message M plus some noise. So everything that is in blue in red are secret and small. So actually we can get rid of this because it's small. And so at the end we have the message. So we see that if the noise is too large, there will be a failure, which means that M prime will be different from M. But this failure is really, really, so the schemes are designed so that these failures are really, really small for honest user. So actually this is extremely unlikely for in-CCA protected schemes. So the higher probability is 2 to the minus 117 for round 5. But anyway, they were an attack that against this in-CCA scheme that were presented by Jan-Peter Danvers et al. In PKC 1919. And so it has two steps. The first step is the failure boosting. So we make a heavy quantum pre-computation to select weak ciphertext. So we just iterate and generate many of them. And once we have one that has a large norm, or it is more likely to create a failure, we submit it to the decryption, and it has a higher probability to give failure. So and any failure gives information on the secrets. And so this attack, we can use our LeakLW framework to integrate the information about about the failure. So we recall that M prime is equal to M plus some noise term. And so there is a decryption failure if the noise term is larger. So here M prime and M are bits. So it fails if it is larger than one half. And we can rewrite it by writing W, which is a vector, and S, which is the concatenation of E and Z, and making some assumptions. And so we end up with inner product between S and W, which is larger than Q/4. But it's not already a hint because we have a larger equal. So it's not exactly perfect or approximate. But actually, so we assume that we know the sign. So we have one chance out of two. And in a concrete attack, actually, once we have one failure, for the other ones, they are likely to have the same sign. So one chance out of two. And then we see that so even if it's larger or equal, we can say that the S is equal to W plus some noise. And so so here it's there is a lattice instance that is easier. So we can actually say that S is equal to K times W plus epsilon. And then we have an approximate hint. So it can be geometrically as I presented in the figure. And so the parameters K and epsilon are given by the parameters, and so they're computed by the attacker. So each time we have a decryption failure, we have an approximate hint. Yeah, one decryption failure equal one approximate hint. So we could use we could reproduce this security estimation from the paper of PKC with our estimation, and it's close. We have a little bit less. We have a little bit more easy attack, but it's really close. And so the more failure, the less security. So we can see that with 2 to the 8 failures, the bit security is below 130 and 30, yes. But actually, so we can do better. This is, if I have some time, yeah, I will present it just briefly. So it's another paper that combines a little bit two things. So the first thing is that once we have the secret, once we have one failure, we can actually use this failure to trigger new failures. So yeah, we have a failure C0 it's a failure because it's close to S, and so we can like change the generation of the weak ciphertext by making a smart selection, and then we can have another failure, and so we take the average, some kind of average to get an estimate. And so the more failure, the more accurate we have an estimate of the secret, and so it corresponds to an approximate hint. Each time we have our estimate, we have S equal to E plus noise, which corresponds to an approximate hint. So once one failure happened, the selection of the subsequent ciphertext is easier. So this is presented here. So it's the extra work for having availing failing ciphertext. So for example, for having one ciphertext, it's very expensive in terms of query and work. But after, once we have one, the number of query and work is dominated by the search of the first one. So this is on a Frodo similar scheme. So actually, once we have one failure, we can see that the security decrease because we can trigger other ones, and then at the end, we can decrease the security. So this is a little bit hand wavy, but yeah. So let me conclude. So I presented a leaky LWE framework, which is a tool that is fun because it can happen in several cryptanalysis, like in side channel cryptanalysis, in decryption failure cryptanalysis, and also in real world cryptanalysis. So it was done with Dana Dashman-Soled, Leo Duca, and Eugene Gong. It was presented in crypto last year. And there is a code available with a small tutorial. So feel free to use it and do not hesitate to contact me if you have a problem, or I'm really happy to help with this tool. There are still many improvements to be done to integrate more hints, to have more side information, either on the theoretical side or on the practical side, like having details on how to include special side channels, etc. So that's pretty cool. Thank you for your attention. I'm happy to take questions now. We have around 10 minutes. I don't know, Pierre, how you want to proceed.
Yes, merci Melissa. Donc là, pour l'instant, j'attends de voir s'il y a quelques questions. Donc effectivement, vous pouvez faire une réaction. Je peux essayer de vous... Alors, je ne sais pas s'il y a quelqu'un qui... Là, je suis en train de faire le tour. Je ne vois pas trop de questions, mais y a-t-il des questions là? Non.
I don't know if there is a
bon, donc moi, je vais essayer de quand même te poser une question quand même. Donc, oui, alors, ce que j'ai compris donc, de la présentation, c'est qu'en fait, faut faire très attention à ces problématiques de fuite ou de side channel ou enfin oui, de fuite, de hints, alors d'indices là pour
ouais.
voilà dans ces choses-là. Donc la question c'est que donc en fait, est-ce que c'est tous les problèmes sont évacués dans le fait que par exemple en Frodo, on régénère à chaque fois une matrice, enfin on génère une
Ah,
clé. Est-ce que parce que là ça a l'air d'être lié au fait que bon ben on a enfin oui, c'est du LWE, mais effectivement, enfin.
oui, je vois du coup le fait qu'on ait un secret éphémère dans Frodo à chaque fois.
Voilà.
En fait, ça dépend si on peut avoir des indices, même avec un secret éphémère, selon avec des attaques par canaux auxiliaires. On peut mesurer une seule fois et en une mesure avoir ce qu'on appelle des single trace attaques. En fait, c'est ce qui est fait dans Frodo, dans l'attaque side channel que j'ai présentée sur Frodo, c'est une
D'accord.
single trace attack. Donc en fait, c'est en une seule trace, on arrive à avoir de l'information auxiliaire. Donc non, ça s'applique aussi pour des secrets éphémères. C'est sûr que si les secrets sont pas éphémères, c'est plus ils sont beaucoup plus susceptibles d'avoir ce type d'attaque.
D'accord. Et deuxième chose, enfin, je sais pas si c'est général que j'avais un peu noté, c'est qu'en fait, quand on va dire le support de l'erreur, là, tu as cité le ntro, enfin, quand des
Mmh.
supports très petits,
Oui. Mmh.
ça peut être plus problématique que les supports quand les supports sont plus grands, ou est-ce qu'il y a...
Oui, oui, ça peut être plus problématique. En fait, ça dépend de la distribution, de l'erreur, du coup, la distribution serait plus petite et donc ça permettrait d'avoir une sécurité plus basse. Mais ça, c'est en général, c'est designé pour que enfin, s'il y a pas d'informations extérieures, c'est designé pour que ça atteigne la sécurité, qu'on veut. C'est juste s'il y a en plus des contraintes, de poids, c'est-à-dire le nombre de 1, qu'il doit y avoir ou, de choses comme ça, là, dans ce cas-là, il faut faire attention.
D'accord. Donc, d'accord, merci. J'ai une question là qui m'est arrivée par le chat de Laurent. Alors, je vais... Alors, soit je... Attends, est-ce que je vois Laurent? Si je peux le... On a un peu de temps, je peux le unmuter. Je sais pas s'il peut. Sinon, je vais te la lire. Alors, bon, soit Laurent arrive à enlever le micro, mais je suis pas sûr.
Ouais,
Ah,
c'est bon. Je ne sais pas si vous m'entendez. Ouais, la question, c'était quand tu introduis tes indices au fur et à mesure, et puis avant de faire ton SVP que tu renormalises,
oui.
a priori, sur tes courbes expérimentales, ça n'avait pas l'air de trop perturber l'estimation de la taille de bloc optimal pour BKZ. Mais à quel point on peut rajouter des indices comme ça au fur et à mesure sans trop perturber ça?
Alors je vois pas trop, donc je vais revenir sur les trucs de, oui, j'ai oublié de mettre les remerciements. Donc sur ces histoires d'approximation, hop. Donc ici, donc c'est-à-dire ça perturbe pas trop. Donc il y a, c'est peut-être à cause du gap